Hey guys, this week we are going to talk about 8.1 in the textbook, areas and volumes. So we're going to talk about how we can use integration to find the areas of shapes as well as the volume of solids. So before we dive into this, let's just recap what we talked about when we learned integration in Calc 1. So what were we doing is essentially we had some kind of curve. Okay, so in this case, I have the curve x squared. And we took a limit as the number of rectangles went to infinity. And we added up all of those rectangles. And when those rectangles went to infinity, this distance, this little width of the rectangle got very, very small, right? And we called that small width dx, okay? And we called the height of the rectangle at a certain x value f of x. So what we ended up getting when we took the limit of these rectangles as n goes to infinity is we got this interval. So in this case, our starting point was 0 and our ending point is 1. And what we're going to do is, to find the area of our rectangle, you multiply length times width. In this case, the width of each rectangle is dx. And the length is just going to be f of x, right? F of x times dx. So that represents the sum of all of these skinny rectangles from x equals 0 to x equals 1. Now, who's to say that we can't integrate along another axis? So typically what we did, or what we're still doing actually, is we're integrating with respect to the x-axis, which means that our dx value, the width of our rectangle is what's shrinking, right? But we can easily integrate with respect to y. So let's look at this shape on the right. So here we have another shape. It's not really a curve, but maybe it's three curves that are bounded by each other. Anyway, what I'm trying to say is that we can also sum up the areas of rectangles along the y-axis. That's no problem, right? And so in that case, this becomes, we still have, we're still going from 0 to 1, but this time we're integrating with respect to y. So what this looks like, we're going from 0 to 1. Our width is dy, and the question is, if our width is dy, what is our length? That's the question. Well, this is interesting because, the length is, it's like a function, right? If we look to the left at our Calc 1 example, the length, the height of these rectangles are constantly changing from point to point on the curve, right? And that's true in this curve too, right? We start out with a pretty small height, and then eventually we get, a pretty relatively high height. So what I'm trying to say here is that we need to replace the length or the height, not with f of x, because we didn't call this function f of x, but we're going to just say that this function is the length function, and we want it to be in terms of y. Okay, that's the key idea here, is that we want our length function to be in terms of y, just like our length function over here was in terms of x, because we're integrating with respect to the x-axis. If whatever axis we are integrating with respect to, we want to make sure that our height function is a function of that variable. All right. And this might make more sense when we go along, but let's just keep going at it. So our first question says, find an expression for the area of the shaded strip in the figure as it would appear in a Riemann sum. So remember, a Riemann sum was just adding up an infinite amount of rectangles, all of equal length, or all of equal width. So how would we set up, if we had to set up an integral here, how would we do it? So the area of the strip, well, it's a rectangle, right? An area of a rectangle is length times width. In this case, the area of the rectangle, we have a width of delta x and a height of 8, right? That's what this guy tells us, that this thing has a height of 8. But how is this shape different from this shape? How are these different? Well, they're different because in this shape, the height is changing. Whereas in this shape, the height is constant. As we move along this axis and add more and more rectangles, the height stays constant. I hope you guys can see that. Let's see. So here's another strip, and we're just interested in filling this whole white rectangle with infinitely skinny rectangles. Okay, so that's what we do when we integrate. So let's set up an integral. Well, actually, part A just wants to know, write an expression for the area of the strip. So the area of the strip, of a single strip, well, the width is delta x, as we said, and the height is going to be 8. So it's just delta x times 8, or 8 delta x might be a better way of writing it. All right. So part B says, write a definite integral to represent the total area of the figure and use this to find the area. So delta x is the same thing as dx when we set up the integral. It's just a very small change in x. So I like to start with that. Because I have that delta x, I know that I'm integrating with respect to x. And that's my width. So my height is going to be, well, it should be a function of x, right? It should be a function of x. Well, actually, let's just write it like this. Maybe I'm going to write it like, how about we just say y of x, right? So the height is y as a function of x, but, the whole thing here is that the height is not changing as we move along the x-axis. So as we start here, this is the beginning part, right? We're going from x equals 0 to x equals 10. So those are my bounds. And the height's not changing, right? As I move along, as I add more and more skinny rectangles in here, the height is always going to be 8. So this is simply 8. No x's are needed here. All right. And let's go ahead and integrate this. So this is just 8x, and we're going from 0 to 10. So this is going to be 80 units squared. Okay. And how could we confirm this with a geometry formula? Well, the area of a rectangle is just length times width, right? The length here is 10. The width is 8. 10 times 8 is 80. So that is how we do that problem. So in this example, we're trying to find the area of this triangle by using strips, rectangular strips in particular. Now you might be looking at this purple strip and you might be saying, Sarah, that's not a rectangle. Are you crazy? Well, what you have to imagine is that this width of the rectangle, that this width right here is getting super, super small, right? And as that thing shrinks down, you can kind of imagine how it'll look like a rectangle, right? Let's just do an example of this. As we get really skinny, it really does start to look like a rectangle. So that's what I want you to think of in the back of your head with these examples. Okay, anyway. Notice how our problem is set up, how the diagram is set up and everything. What we're asked to do is we're asked to integrate along we're calling it the h-axis. You can think of it as y. Because we can see this delta h here, right? This is representing the very small change in width of the rectangle. So to find the area of each strip, well, we know that the width is going to be delta h, right? We can see that pretty clearly from the picture. But what's the length? What's the length of the rectangle? You got to ask yourself, is length a function of height? Let's write that down. This is really important. Is length? Oh my God, I can't spell length. It's really late right now. Let's just say L. Is L a function? A function of height. Is length a function of height? What does that mean? That means that the length is going to change as the height changes. Is that true? Well, consider this. Consider a rectangle all the way down here. Now we still have the same width of delta h, that's fine. But how is the length different in this orange rectangle than in this one right here? Is the length different as we move along? Well, yeah, it is, right? The length is changing as the height changes, right? As, if we start at the very bottom and we start integrating upward, we can see that as our height increases, the length actually decreases. Look how tiny this one is up here. Okay, so here's the thing, okay? L is a function of h, and so, I can't just put a single number there. It's not going to make sense because remember, with integration, we're integrating along an infinite interval, right? We want to add up an infinite number of rectangles, so it's not going to make sense for us to just have one single length here. I hope that's clear. But anyway, so this is like our width of the rectangle. This is our length. And why am I putting it as a function of h? Because that's what I'm going to integrate with respect to. That's why I'm doing that. All right. So let's set up our, so we want to actually be able to put this thing in an integral, right? Now, delta h is simply dh. That's no problem. Maybe I'll fill it out down here so we see. So we know the dh part, but we want to know what goes here. What is our length in terms of h? And by the way, where are we integrating from? Where do we start and where do we end? Well, we're integrating with respect to h. So we're starting at 0. If you imagine that this is like on the xy axis, just chilling here. Just imagine that this is on the xy axis. We start at 0, 0. And we are slowly building the rectangles up, right? And we're moving up, right? So we're going from 0 all the way up to 5. Okay, so I might redraw this because it's starting to look a little bit messy. I am going to do that actually. Let's just redraw, regroup. So here is my here's my little rectangle. Little bitty rectangle. And the guy has some height or some length. And this thing, we said it's 3. We're not really given units here, but that's okay. This is 3. And this is 5. Here's our little strip. Okay, so, and by the way, let's just write that this is an arbitrary height of h, right? Because the goal is to form a relationship between h and L, because I only want h's in my integral formula. I don't want this. Like, what does that mean? I don't know. I just want h's. So, how do I do it? Well, there's a trick. The trick is similar triangles, okay? So, I don't know if you guys, well, those of you that had me in Calc 1, you probably maybe remember this video. I don't know. But remember we were doing optimization problems. We had this cone, and then there was a smaller cone in it, and we used similar triangles to relate the radius of each cone. That's what we're going to do here, okay? That's the idea here. So we need to, first of all, let's draw this guy. So we have this guy. He has a base of L, and he has a height of, well, he doesn't have a height of h. That's not how tall he is. He actually has a height of 5 minus h, right? Because maybe if I draw it on this side, you'll be able to see it more. If the whole thing from top to bottom is 5, and just from here to here is h, then of course what's left over is going to be 5 minus h. All right, so this thing has a height of 5 minus h. Cool. We're getting somewhere, I think. And now what's cool is that we have this giant triangle whose height and base we know that the base is 3 and the height's 5. And this is really helpful for us because now, since similar triangles, the sides are proportional to one another. So, basically one is just a scaled up version of the other. And so we can set up a proportion, basically, to get L in terms of h. That is what we want, you guys. We want L in terms of h. So let's do it. I'm going to erase some of this stuff. And maybe I'll just put this off to the side here. So what is our proportion going to be? So we can compare side to side with ratios. We can say the base is to the height as the base is to the height. So we can do it like that. Sorry if you guys just heard a cat. That was my cat. She's mad that I'm not paying attention to her. Okay. So now what we can do is we can get L in terms of h. If I multiply both sides by 5 minus h, let's do that. I get this nice relationship. The relationship is, therefore, L is equal to 3/5 5 minus h. All right, so this is a key idea in this section. That length and height are related in this way. And now what's cool, you guys, is that we can set up our integral. This is so cool. I think it is, at least. So, what did we have originally? Originally, our answer for... Well, actually, let's write out our answer first. I'm getting ahead of myself. I'm erasing all of this stuff. Erase, erase, erase. I never give myself enough room. You'd think I would learn by now with, making all these videos, but, some people never learn. I guess I'm one of those people. So, okay, perfect. So what's our answer for part A, by the way? If you need to, pause the video. Okay, what is our answer? Well, our answer is just going to be 3/5 5 minus h times delta h. Right? This is the area of each strip in terms of h. Right? This was the width, and this was the length in terms of h. Cool. Let's integrate this guy. All right, so we're putting 3/5 5 minus h in there. Awesome. And then dh, we can't forget about that. That is replacing the delta h. Okay, cool. All right, so let's go ahead and pull this constant out. And we know how to do this. So 5 minus h with respect to h, well, this guy, when we find the antiderivative, is just 5h. Then we have minus h squared over 2. And we're integrating from 0 to 5. And then basically, when we plug 0 in for h, it's just all going to go to 0. It's going to end up being minus 0 when we do that by the fundamental theorem of calculus. So let's go ahead and simplify this guy. We got 3/5 25 minus 25 halves. And if I distribute that guy in there, I end up getting 15, 3/5 times 25, minus... Let's see, 3/5 times 25 over 2. We get 15 over 2. All right. So we have 15 minus 15 halves. And what is that going to give us? So we have 15 minus 15 over 2. So this is going to be equivalent to 30 over 2 minus 15 over 2, and that's just 15 over 2. All right. So that is our answer here. That's the area of this triangle. Now, how can we confirm that this is true? Well, we can just use our area formula for triangles. Remember that? Area of a triangle is base times height over 2. Here, our base, well, I erased it, but our base was 3, and our height was 5. And so 3 times 5, 15, divided by 2 is 15 over 2. Use integration to find the area of our semicircle of radius 7 centimeters. So the first thing we need to do is we need to put this thing on the coordinate plane and then talk about upper and lower bounds and everything like that. So what I can do is I can make, it's not perfectly drawn to scale. Let me see if I can do this a little bit better. I can make this guy. So this could be 0, 0, the middle. And then this guy right here could be negative 7, 0. And then this guy could be 7, 0. All right. Circle of radius 7. All right, so how are we going to do this? Well, we know that, what we're trying to do basically is we're trying to sum up all the rectangles, right? All these infinitely small rectangles from x equals negative 7 to x equals 7. So let's go ahead and set up our integral like that. So we're going from negative 7 to 7. And we know that we're integrating with respect to the x-axis. So our width of our rectangles are going to be dx. And then our height of our rectangles, well, we can just say that the height is y, but remember we want it in terms of x. All right? So how do we get the height at any point in terms of x? Well, we can use a little trick, and this is the trick that I'm going to use. So what I'm going to do is I am going to draw out a radius all the way to here. So this is a radius, right? And we're told in the problem that the radius is 7. Perfect. All right. So then we can just drop down a height or a y value. So that's going to be our y value. And we know that this distance right here is going to be x. All right. So how do we establish a relationship between 7, x, and y? Well, we can just use the Pythagorean theorem, right? So this is a right triangle. So we can say x squared plus y squared is equal to 7 squared. So we get y squared is equal to 49 minus x squared when we move everything over to the right side. And then if we square root both sides, we get that y is the square root of 49 minus x squared. So we have just made y a function of x. So that's what we're going to put right here. This is y of x. Y as a function of x. All right, so let's go ahead and replace that with square root of 49 minus x squared. So we have the square root of 49 minus x squared dx. So again, what I just found here is my height for a given x value. And what I can do at this point is I can use that table of integrals. And let's see. Which one are we going to use here? Well, the first one I can use is 4-30, which tells me that if I integrate the square root of a squared minus x squared, that's going to be a half x square root of a squared minus x squared. Oh, I'm running out of room here. Let's actually write it down here. Let's write it down here. So we have this guy. Okay. All right. So in this case, our a is going to be 7, right? Because we're trying to replace what we have with this formula right here, square root of a squared minus x squared. So in this case, a is 7. So if I plug in all of that stuff into my formula here, I just get that this is equal to 1/2 times x root 7 squared minus x squared under the radical plus 7 squared, and then integrate 1 over the square root of 7 squared minus x squared dx. All right, so far so good. And now what I'm going to do is I am going to now use, I'm now going to use 4-28 to evaluate this guy right here. So let's write that out down here. So we have 4-28, and that's telling us that the integral of 1 over the square root of a squared minus x squared dx is just equal to sine inverse of x over a plus c. All right, so in this case, we have, this is going to be equal to 1/2 just simplify that to 49 under there. And so this is going to be plus 49, and then we can multiply that by sine inverse. In this case, our a again is 7, so that's going to be x over 7. All right, great. And now we can evaluate at our bounds. So again, I'm going to just erase this so it's a little bit cleaner. So I'm going from -7 to 7. So let's put that in here. We're going from -7 to 7. All right, so if I plug in 7 anywhere I see an x, I get 1/2 7 49 minus 7 squared plus 49 times sine inverse of 7 over 7, right? And then we're going to subtract the when we plug in -7 in for x. So we have minus -7. Again, I'm just plugging in -7 anywhere I see an x just by the fundamental theorem of calculus. So this is going to be minus -7 root 49 minus -7 squared plus 49 sine inverse of -7 over 7. So let's go ahead and simplify this guy. Well, what's cool is that this guy all under the radical goes to 0, right? 49 minus 49, that all goes to 0. And likewise, let's see. We have something under the radical that goes to 0, 49 minus 49 again. So that all goes to 0. And then sine inverse of 7 over 7 is sine inverse of 1, which means, hey, which angle has a sine value of 1? And that's the y value. So that's going to be pi over 2. And this guy is going to be negative pi over 2 because that's the sine inverse of -1. All right, so what we have, let's go and carry this down. So we have 1/2, and simplifying the inside when those zeros cancel out, we have 49. Sine inverse of 7 over 7, remember, was pi over 2, minus 49 sine of, or sorry, that should be 49 times negative pi over 2. All right, so cleaning this up on the inside, I get 49 pi over 2, and then plus 49 pi over 2, right, because these double negatives. And what I end up getting is a half 98 pi over 2, which is going to give us 1/2 times 49 pi. So I end up getting 49 pi over 2. So it's the area of that semicircle, and that's from integration. So let's use our geometry formula to double check this. So our formula for a circle is pi r squared. Our circle radius was 7, so area is pi times 7 squared, so it's just 49 pi. And remember, that's the area formula for a whole circle, so a semicircle is going to have an area of 49 pi over 2. So yes, we did get this right. So that is how we found the area of the semicircle using integration. So let's bump it up a dimension. We've been talking about two-dimensional objects finding the area. We can do a very similar thing to find the volume of a three-dimensional object. So consider this box right here. We know what the volume is because we know geometry, right? We can just multiply length times width times height. So we can just say, well, you know, the volume is going to be 6 times 4 times 3, units cubed, basically. But how can we do this with calculus? So this is the idea. What we're going to do is we are going to imagine a slab that's infinitely skinny in this box. So let me do my best to try and draw this. All right, so we have this guy right here, and maybe it goes like this, and like this. Okay, and maybe it goes like this. Okay, try to imagine that this is a good looking solid slab. So let me color it in a little bit so you guys can see it a little bit better. So basically, you want to imagine that you're cutting this slab out of this box, and it has, you know, some very, very small thickness to it that we are going to call dx in this case, right? And so this is a very similar problem to the area problem, right? So what we're going to do here to integrate this thing, we are going to integrate the width with respect to x times, well, actually, how about we just say it like this. We want to find the surface area of that cross section with respect to x times the thickness of it, which we'll call dx for how thick this thing is. All right. So, you know, if I was to kind of like take this cross section off to the side and draw it, let's do that. So maybe we'll keep it in green. Let me draw it off to the side just so you can see it a little bit better. Okay, so it looks like that. So it has some thickness to it, and we'll call this thickness dx. Okay, and then it has a length and a width. And the question is, how can I write the length and the width in terms of x? Do I need to? Well, the question you should ask yourself is, if you're starting right here with a slab, so you put an infinitely skinny slab in the very front of the box and you move along this axis, right? You're just adding more and more and more slabs until you get to the very end of the box. So the question is, are the length and the width changing as we move along that axis? And the answer is no, they're not changing, right? The slab that is back here is going to have the same length and width as the slab that is in the very front, right? There's no change here. And so basically what we have is the following. So we have the integral, and we're starting, if we imagine this on an axis, we're starting at 0, right? And we can see here that the axis that we're moving along is 3 units long. So we're starting here at the very front of the box at 0, and we're moving all the way to the back of the box, 3. So we're going from 0 to 3, and the surface area in terms of x is just length times width. We don't need to even add an x there because, these are constants. They're not changing with respect to x. Times the thickness, right? So I hope you can see the volume here. Length times width times the infinitely small thickness. And so what we end up getting is we get an integral from 0 to 3 of 24 dx. Let's go ahead and integrate this guy. Well, this is just simply going to be 24x from 0 to 3, which is just going to give us 24 times 3, which is 72 units cubed. Okay. So that is how we found the volume with calculus. And you can just find the volume, like you normally would with a geometry formula in this case, because the length and the width are not changing as we move along this axis over here. So 6 times 4 times 3 is going to indeed give us 72 units cubed. So pretty cool. All right, let's do a problem like this. So you might have a problem like this on your homework. We want to give an expression for the volume of the slice used in the Riemann sum representing the total volume of the cylinder. And then we want to write a definite integral to figure out what the volume of the cylinder is. So it looks like since they're giving us that the change in x is along this axis right here, this is the axis that we're moving along, right? And since this thing is a cylinder, we're not going to use little box slabs. We're going to use little circular slabs, as you can see right here, this little slab. So, okay, so now we need to figure out what is the volume of each slice of this little slab that I'm pointing at. Well, remember, we want to write this in terms of x because that's what we're integrating with respect to. So we want to write the integral of ax dx, where a of x is just the surface area of that disk that we have. So what is that going to be? Well, we know the area of a circle is pi r squared, and the question you want to ask yourself is, what is r? What is the radius of this little piece right here? What is the radius of that piece in terms of x? Well, the radius is just 4, right? Because we can see here at the top that the diameter is 8, therefore the radius is 4. And why am I not writing it in terms of x? Well, because look, as we, if we start right here, if we start here and we add a disk, right, you can imagine this has some thickness. So we add a disk and we add a disk and we add a disk and we keep going up right there. Is the radius changing at all as we move along the axis? Well, no. No, the radius is going to be constant, actually. And I hope you guys can see this, that the radius is not changing with respect to x as we move along the x-axis. So with that being said, this is simply a of x is just simply pi times 4 squared, which is 16 pi. Okay? So the volume of the slice is the surface area, which is 16 pi, times the thickness, which we're calling delta x. So that is this part right here. Volume is surface area times thickness. All right, so let's evaluate this integral. So the total volume over all disks. Where are we integrating from? We're integrating starting right here, right? We added an infinitely skinny disk right here. It has, a thickness of dx, but it's very thin, and we keep adding disks, right, all the way up until this point. Okay, so we start at x equals 0 all the way up to x equals 11. So we're starting at x equals 0, we're going up to 11, and then we're adding up all of the slices, the volume of each slice. So that's going to be 16 pi times delta x, which, since we put this in an integral, we're going to call it dx. All right, very nice. So we are summing up all of these little volumes. And so when we figure out what this integral is, let's go ahead and do that. So we're going from 0 to 11 of 16 pi dx. So if I can pull out a 16 pi if I want to. And then this guy is going to turn into x. We're evaluating from 0 to 11. And we simply get 176 pi. So that is the volume of this cylinder right here. Use horizontal slicing to find the volume of each disk, then find the volume of the region by integrating. All right, so let's draw a little sample disk in our cone here. Maybe it looks something like this. It has a little bit of thickness, and I'm going to call that thickness dy. So you can imagine that this is like maybe like a coin or something. It's just a very skinny cylinder, and we're going to call its thickness dy. It's also going to have a radius, which we're not sure what the radius is right at the moment. But we know that the diameter of the base of this cone is 10 centimeters. And that means that the radius is going to be 5 centimeters. So let's just label that here. Now, how is this problem different from this problem? Well, we can see that, here we're integrating along the horizontal axis, and we started here, right, and we just kept adding more and more of these skinny disks, right? But the thing is that the radius never changed, right? The radius remained constant. However, in this example, we can see that the radius is changing as the height changes. So like if I'm way up here, for instance, this disk is going to have a very small radius compared to this disk, or even a bigger one down here. So that's going to make our problem a little bit more involved, I guess we can say. So what is going to be the volume of this disk right here? Well, it has a thickness of dy, right? And we want to multiply by the area of that circle, so the area of the base, basically. And I want it to be in terms of y, because my thickness is dy. All right, so this is going to be the volume of a disk, or is it disk with a C? I'm not sure, but anyway. So this is going to be the volume of the disk. And so the question is, what is A of y? Before I put this in an integral, what is A of y? Well, remember, the area of a circle, so the area of that base, is going to be pi r squared. But remember, the radius is changing with respect to y. So we need to put the radius in terms of y. And how do we do that? Well, we're going to use similar triangles in a similar way to what we did. Where did we do it? We used similar triangles right here. So we're going to do this in a similar way. And let's see if we can visualize this. So let's see, we have our first triangle right here, this guy. We can kind of see that. We cut that little triangle out of the cone. So let's draw it down here. So that guy has a base of r. And what's the height? What is the height of this guy? Well, let's say that, you know, from here to here is y. And so just like before, the height is going to be 5 minus y. So this guy is going to be 5 minus y. All right, so we got that triangle taken care of. And then we want to look at the bigger triangle. So the bigger triangle, it's going to be like that. So this purple triangle is going to have a base of 5, and we can see that the height of that bigger triangle is also going to be 5 centimeters. All right, so let's go ahead and set up a proportion. So we can say that r is to 5 minus y. So the base is to the height of the orange as the base is to the height of the purple. And all we have to do is solve for r. So multiplying both sides by 5 minus y, we just get that r is equal to 5 minus y. So now we have r in terms of y, which is what we wanted. All right, so now area in terms of y, I'm going to replace r with 5 minus y. So that's 5 minus y squared. All right, and now we can actually put this in our formula. So let me erase some of this stuff and rewrite. So therefore, the volume of a disk, of a single disk, is going to be A of y, so pi times 5 minus y squared. So again, this is the surface area of the base times the width, or sorry, times the thickness, which is dy. And actually, maybe we should say, yeah. Well, actually, we'll say that this guy let's wait to put this in the integral. Let's say this guy is delta y, so this is going to be times delta y. So that's the volume of our disk. Now when we put it in the integral, we're going to change that guy to dy. So what am I integrating with respect to? Well, I'm integrating with respect to y, right? I'm adding disks along this y-axis, right? And I'm starting at the bottom, and I'm just moving up until I get to the very top right here. So I'm starting from 0 until a height of 5 centimeters, right? And what am I integrating? Well, I'm integrating pi times 5 minus y squared. Instead of delta y, I'm putting dy. And actually I wrote this wrong. This should be 5 minus y all squared. Sorry, guys. All right, beautiful. Now let's go ahead and evaluate this integral. So I'm going to go ahead and first pull out a pi, and I'm going to expand this 5 minus y squared. All right, now I'm going to go ahead and integrate. So this is going to give me, when I do that, I get 25 pi minus 10y squared over 2 plus y to the third over 3. And I am evaluating from 0 to 5. Okay, so plugging in all of that, we get pi times 25 pi minus 10 times 5 squared over 2. This was not 25 pi, this was 25y. I'm sorry, I'm making these errors here. Okay, sorry guys. Okay, so this is going to be that minus that plus 5 to the third over 3. And then if we subtract off, if we plug in 0 for all of those y's, all of that's going to go to 0. So we don't really have to include that there. And when all is said and done, and you simplify this, you should get 125 pi over 3. And that's our answer. Okay, so in this example, we want to figure out the volume of this hemisphere, this half sphere. We want to first figure out the volume of each of these individual slices that we can see in the picture. So the first thing is the volume of the slice, or the volume of the disc, however you want to say it. We can see that it has a thickness of delta y. So remember that the volume in general is just the volume of the surface area of the base times the thickness. So here, since we're cutting circular slices, the surface area of the base is going to be pi r squared times the thickness, which is delta y, right? So this is going to be the volume of the disk. The volume of the disk. Now we want to figure out what r is in terms of y, just like the previous problem, because the radius is changing as we move higher and higher up the disk, or up the hemisphere. So how do we do it? Well, let's imagine that we draw a triangle right here, right? And this triangle is, it's gonna have a radius, right? We're not really sure what it is. So we'll call that radius r, and we'll call the height of it y, okay? Then, since we have a hemisphere here, the middle to the edge of the hemisphere is going to be the radius of the base. And the radius of the base is 8 millimeters. So this guy is going to be 8. And what we can do here is we can actually use Pythagorean theorem to to write r in terms of y. All right, so here we go. So r, again, this is the radius of a disk. So r is the radius of a disk at height y. All right, and we can say y squared plus r squared is equal to 8 squared. Therefore, r squared is equal to 64 minus y squared. And so r is equal to the square root of 64 minus y squared. All right. Therefore, the volume of the disk is going to be pi times r, and r in terms of y is just going to be, oh, I forgot to square root this. It's going to be the square root of 64 minus y squared. So pi r squared times dy. All right, so that's the volume of each disk. And what's cool here is the square and the square root can cancel each other out. So let's just say this. Let's just say pi times 64 minus y squared dy. So that is the volume of each disk. Now to figure out the total volume by summing up the infinite disks, we're going to go from 0 all the way up to 8. So again, let me try to illustrate this here. So we're starting at the very bottom of this guy. Right, we're starting at the very bottom. We have a very, very small thickness here. And we're starting from 0 and we're moving up all the way till we get to the very top. So we're going from the height equals 0 to the height equals 8. And we're going to have 64 minus y squared times dy. And actually, I should have put delta y right here because we didn't put it in the integral yet. So let's do that. Delta y. Now when I leave the integral, when I put it in the integral, I'm just going to use dy. Okay. So let's go ahead and evaluate this guy. Oh, and I should mention that we have pi times this. Okay, so let's evaluate this integral. So if I pull out the pi in the front, I'm just left with 64 minus y squared dy. All right. And so this is going to leave me with 64y minus y to the third over 3, and I'm evaluating from 0 to 8. And what this is going to end up giving me is pi times 512 minus 512 over 3. And so I end up getting 1024 pi over 3. And that is my answer right here. You should also confirm your answer by using the geometry formula. So the volume of a sphere is going to be 4/3 pi r cubed. All right, so what you should do is you should see with, the radius of the sphere is 8, right? So you should plug this in and see if when you divide it by 2, because we have a hemisphere, if you indeed get this guy. All right, so we can do this without calculus, but I would just use that to check your answer.